Welcome everybody for today's webinar. My name is Ruby Karat and I'm the Partnerships Manager at iWave. And today's webinar is a joint effort with our technology partner NXP, and it's being titled Security Suite for NXP i.MX Applications Processors. Few housekeeping items before we get started with the webinar. The webinar is scheduled for 1 hour, including the Q&A. All dial-in participants are muted to enable the speakers to present without interruption. Recording of the webinar and slides will be made available to all attendees in 2 days. In case of any questions, please use the chat button and you can post your question. So presenting today is Silvano Di Nino, who is a software engineer at NXP. And from iWave side, we have Taufik Ahmed, Product Marketing Telematics. A quick look at the agenda for today's session. We start with understanding the i.MX trust architecture features, followed by getting to know the security features in NXP's i.MX SoC. Then we learn more on strategies to secure the IoT devices and more details on iWave's security suite architecture. Finally, we have the Q&A session. On right-hand side of your screen, you should be able to see the chat box. Feel free to post a question at any time during the webinar. When we get to the end of the webinar, we will start going through the questions during the Q&A session. Hopefully, we will have enough time to go through them all. And if we don't, we can always reach out to you later. So without further ado, sit back and enjoy, everybody. I will pass it over to Silvano. The floor is all yours, Silvano.
Thank you, Ruby. So again, thank you everyone for joining. So my name is Silvano Di Nino. I'm a software lead for i.MX and Layerscape software security drivers and IPs. So we are mainly developing trust zone software stack like OPTI, and we are also developing the CAM driver for the i.MX and Layerscape SOC, and some development also on our middleware software like the OpenSSL or secure storage. Our team is actively upstreaming content to the OPTI and CAM and Linux drivers, and we are both maintainers for the OPTI i.MX and Layerscape subsystem in OPTI upstream community, as well as the Linux CAM driver maintainer for both i.MX and Layerscape devices. So today I would like to present you some of the security features of the i.MX SOC family. Just as a disclaimer, it's not a full presentation of the i.MX devices. I will recommend you to go to nxp.com for that. And it's also not a in-depth security presentation. It's really to give you an overview of the security features. When we talk about security on IoT devices, there are the main concerns that pops up is large attack surface, commercial theft, so IP protection, espionage, trustworthiness of the devices, data integrity and protection for like personal attacks and privacy invasion. IoT devices are also placed in location where it's easy to attack them. It's not like a big server or a data center. So physical attacks is also a concern, and also the expectancy of the device increases, and so it's also a concern to update the software running on the device in a safe and secure manner. So if you look at an embedded system, the typical attack are shown here. I will not go over everything, but basically the main concern is bypassing the boot security checks, eavesdropping on the communications, external code data access, so DDR eavesdropping or clone or tampering of the DDR. Then we also are looking at physical attacks on the power and reset, so basically glitch attacks. Reminiscence of data when we do a cold reset, they can be also attacks like that, and bypass of the hardware firewalls with malicious firmwares. I'm gonna just present you some of the i.MX security features. Our secure solution is scalable across our i.MX family that range from the i.MX 6s up until the i.MX 8. So if you look at it, you have a variety of security features that help prevent the attacks that I just talked to you about. I'll go over there in more details. But if you look at that, we have all our cryptographic accelerators. We do have RNG. We do have runtime integrity checkers. We do have trust zone. So all our system on chip are ARM based. So we do have trust zone enabled on both Cortex A core or even trusted M core. Some of the families like the Quad Max and the Quad XP do support a secure enclave that will offer automotive grade SHIE extension, security hardware extension for automotive use cases. Of course, we do have a secure boot that we call iAssurance boot that support both RSA and ECDSA, as well as encrypted boot. We have secure storage. We have temper detection, both for pin, passive and active pins, but as well as also voltage and frequency detection. We do have inline encryption, secure debug, manufacturing protection, and resource domain controller. The secure solution on i.MX and Layerscape is referred as the trust architecture. We did have several versions of the trust architecture. We are at trust architecture number 5. So if we go into the feature set, so as I said, we have the trust zone. This is useful to isolate secure critical software. The trust zone is obviously an ARM extension, and we are leveraging that with our enablement software that is running Opti. As I told you, we are maintainers of our i.MX and Layerscape architecture, and we are making contribution to the open source and updating with new system on chip. We are updating the support for Opti. The iAssurance boot, this is our secure boot. We do support RSA, CDSA. We also have a revocation mechanism. We can revoke up to 3 keys. So if one of the keys is tempered or compromised, it can be removed and revoked from the boot. For software protection, IP protection and confidentiality, we do support encrypted boot. It's AES 256, and the encrypted boot, the way it is done is basically it's tied to the chip, meaning that we can protect against cloning. Secure storage is basically tied to our temper detection event. It's secure RAM inside the chip that gets erased, zeroable upon temper events. That can be zeroable upon temper events. This is really useful when we want to make sure that the secrets gets no longer accessible once the temper gets detected. Of course, we have hardware cryptographic acceleration. This is the CAM engine, basically for most of the known algorithm. Secure real-time clock. Again, this is a clock that is protected against tampered. It can run on secure world. and it's useful for DRM or secure time kind of application. And again, we do have a random number generator that is certifiable by NIST. I talk about firewalls. This is another aspect of our architecture is the possibility to isolate processing domains into different domain of execution. This is done both by, we have several flavors of our firewalls, CSU, RDC. The goal is basically to isolate CPU with some peripherals from execution. So we could see Cortex-A with some peripherals that is isolated from another domain, that probably Cortex-M with other peripherals. We can also build a kind of hardware flow that is also isolated from CPU. The good example is DRM with secure video pipeline, where we could decrypt, encode, and display without intervention of the CPU through the RDC. Of course, we have content protection. This goes with HDCP support with HDMI, but also we are building application like wide-line play ready on top of the TE. Secure debug. JTAG can be a way to also get access to the code and to manipulate the code. So we do have features that disable the JTAG or to restrict access to JTAG with a password or a certificate-based negotiation. I talk about the tamper detection. So it's both monitoring alarm of security violations for integrity checks and alarms. Device configuration. So so there are life cycle, what we call life cycle for the device. That when we start with an open configuration, that is, as I said, open for there is no secrets, there is no authentication, and the development is made easier. And then we move to the life cycle until the closed life cycle. The product is secure, authentication is enforced, secrets are being used and protected. And then we have the other way around when we need to return the chip. So we have field return life cycle that will also destroy the secrets and make them unavailable to the software. This is a really simple explanation of our software stack. So as I said, we do provide in our base enablement that is available on NXP.com. We do support Linux and TE. So we, as I said, we do support Opti that is integrated in the Linux, and we are optimizing for the NXP cam driver and NXP temper detection and stuff like that. We do support also some middleware for let's say disk encryption for DMCrypt. We have added support for cam driver with black key encryption, and that is tied to the DMCrypt. And we also have are working on exposing cryptographic operation through or OpenSSL or PKCS11 type of interfaces. I just want to finish with one note. Security is not one solution or one solution that fits all issues. So it's really a discussion on what the assets needs to be protected, what's the content, and what's are the threat model. So I will encourage you, if you have a question, we do have an i.MX security questionnaire that will help you go through your requirement and offer you some guidance. This is provided by our system engineering team. So I will recommend that we reach out to your sales representative for that. Along with this, there is a security checklist that can be provided to you as well. It's basically the list of all the things that you should be looking at with application notes to help you on how to enable a certain aspect of our software and hardware, like the authentication boot, or the disk encryption, the blobs. So there is a, it's not it's quite exhaustive list of things that we should look. Saying that, I'll thank you for your attendance, and I will leave it to Tofik to explain you how iWave is making use of our enablement and for software suite.
Thanks a lot,
Thank you.
Silvano, for the very detailed overview of the security features available on the NXP i.MX SoCs. So now going a bit deeper into why security and in terms of how the iWave security suite builds on the NXP features available on the processor, and how we, with the security suite, speed up your security development is what I will be covering in the next few slides with a more detailed process and overview of the individual security features. So first and foremost is definitely the need for end-to-end security in embedded solutions. So there is no gap that can be excluded, be it your sensor or your connectivity. So to just give a high example, so a few years ago, a group of hackers used a rather unconventional method to break into a casino. And how they did that was via an internet connected thermometer in an aquarium, where they were able to get the complete high roller database with all the sensitive details. So this just shows that even a simple thermometer cannot be excluded as just an IoT product. Security has to be taken care across all components. And how iWave builds this security suite is with the hardware root of trust. The hardware root of trust forms the basic component providing the security perimeter to your connected device. The hardware root of trust is the foundation which we depend on to secure all the operations of your computing system, which contains the keys for various other security functions. So the i.MX SoC is inherently trusted and makes this as a base of chain of trust. And now looking at the different security layers which you need to take care of. So on an end-to-end approach means extending security mechanisms from the device to the cloud to the application. And each of these levels uses different protocols and standards to achieve security. Starting from secure boot, which takes care of loading the right firmware on your embedded device, to the secure OTA, which is responsible for a firmware update or an application program update on the field, or it can be a simple device tampering. How do you take care of your device not being tampered on the field from the mechanical enclosure point of view? So it is the security suite aims at giving a holistic view of security on the device from across all the different layers of your embedded system. Now, I have highlighted in the previous slide. So there are three key interfaces you need to take care of security on. The silicon, which is the i.MX SoC, the device level, and the interface level, be it the wired or wireless. So the silicon level security prevents attacks and threats on the hardware device, where essentially the root of trust comes in. Second comes the device level security, where you prevent attacks such as the storage control, the data encryption, the key management, and various other parameters on the second phase. And last is in terms of the connectivity to the external world, where you have interfaces such as your CAN in your connected automotive, or Ethernet in your industrial application, or in IoT devices, you have the various wireless connectivity options such as Wi-Fi and LTE. So these are the various layers where you need to take key consideration of security in your product design. And previously, security was being considered as only in the product design phase. So the design and development of an embedded system is where people trust the most, and the embedded system development company controls the design process and considers security as part of the standard development procedure. However, there has been a long growth to it. It is just it's not a parameter that has to be taken care of only in the product design phase. It goes all the way from the design, the provisioning, and the field update. So there are different security features which have to be taken care along your product life cycle. As soon as it is designed to maybe 7 years down the line, security is a key consideration throughout the complete life cycle of the product. Now going a bit deeper into the key security features, correct? So let me just give you a big overview of what are the features available. Silvano did touch upon a few of these functions available on the i.MX SoC, but maybe I'll just give a bit more detail on how the process takes place. The secure boot basically helps the device to resist attacks and infection from malware. It ensures that the boot technology and the operating system are legitimate manufacturer version and have not been altered by any hacker. The next comes the crypto function. The crypto function takes the arbitrary amount of data input and produces a fixed amount of enciphered text called a hash value. The hash value is then stored instead of the password. So instead of having just a password to verify the user, the hash created by the crypto function is a much stronger way to secure your system. The file system encrypt and decrypt is another terminology for the secure data storage, where encrypting the file system partitions during flashing and during booting, the complete data will be decrypted such that no one externally can access the data. And the OPTI, which is the open source trusted execution environment. The OPTI basically provides an isolated environment ensuring code integrity and confidentiality. It adds a additional layer of security between your normal world and your secure world. And onto the right, so it's where you have the higher level features in terms of your connectivity or in terms of the different third-party updates. So your OS hardening is basically the process of securing a system where we reduce the surface area of vulnerability and in terms of attacks. Wi-Fi security in terms of access control, in terms of the security layers available on Wi-Fi connectivity, and the access control to different types of clients being connected to your device. And then we have the various third-party mechanisms such as the OTA updates, the WOLFSSL TLS libraries, or such as the firewalls. So all these are like the complete picture of the security functions which are required to completely take care of security on your embedded device. Now to get going a bit deeper into the security suite architecture, which is designed by iWave and how you can integrate it into your embedded device. So at the base of your design is your i.MX SoC, which forms the support for the AHAB, the tamper detection, the crypto engines, and various other security features which Silvano told from the different portfolio of NXP i.MX6 SoCs. And next comes the crypto drivers, the tamper detection layers, as well as the high assurance boot. So what the iWave security suite does is it provides the value addition through the APIs, acting as an interface between your end application, the Linux drivers, as well as your third-party providers such as WolfSSL and MENDER. So the iWave security suite integrates the APIs necessary for all these security functions and enables you to call these APIs without needing to build the complete driver support or to go through the software development again. Now just going a bit deeper into secure boot, which is one of the key security functions available in the i.MX and is highly employed across various embedded systems. So the secure boot is a process where your OS boot images and code are authenticated against the hardware before they are allowed to be used in the boot process. The hardware is set up beforehand in such a way that it only authenticates code generated using security credentials you trust. The secure boot using AHAB is based on two keys, so your public key and your private key, and consists of two key main components, which is the AHAB library ROM and the code signing tool. And the security with the ROM and the AHAB form the trusted software components and are used to establish the secure boot chain. Now going a bit deeper into the process of how do we sign your firmware, correct? So basically the host PC includes this CST tool. The CST package includes like the public key and private key generation scripts under a keys directory, using which the hash of the image is computed and encrypted using the private key, which will provide the signature. This hash contains the HAB data, and it contains the CSF, and it completes the complete certificates. The signed image is then loaded onto the flash, where the cryptographic hash is burned to a one-time programmable e-fuse to establish this root of trust. So your root of trust is basically generated using this complete signing mechanism. Now this is your target platform and how your boot process is generated. So the secure boot process starts with the ROM authenticating. The first image in the boot flow, which is typically a bootloader such as a U-boot or the second program loader or a custom implementation. On the target platform, the AHAB evaluates the SRK table included in the signature by hashing it and comparing the result to the SRK fuse values. If the SRK is successful, the root of trust is established and the remainder of the signature can be processed to authenticate the image. If the authenticity is okay, the software image is executed, else the complete boot is aborted. So this is a base version of how the secure boot is taken care of with the iWave security tool. Now, as I mentioned before, in terms of the building the chain of trust, so information has to be passed on from layer to layer and has to be exchanged confidentially between the different components. And the chain of trust is this only way to ensure that no hacker has interfered in this communication chain. So this is the task of root of trust and why it comes in and becomes the building block for major secure storage and cryptographic operations. And to make it very reliable, a hardware implementation is what is most trusted upon, which is immune to hardware and malware attacks. Through this use of the signing and the trusted elements, secure boot establishes a chain of trust which boots the system securely and validates the integrity of the software. And once the initial bootloader is authenticated and executed, the chain of trust can be continued by authenticating each of the next loaded image before executing it. For example, the boot ROM authenticates the U-boot, the U-boot authenticates the Linux kernel to the file system, and so on. So this is a key, like chain of trust is one of the key terminologies or concepts which helps you establish the complete dependency from layer to layer and establish confidentiality between the different layers. Now going a bit deeper into the secure storage, right? So on the bottom, we have the hardware layer, like where your i.MX SoC comes in, which contains the CAM module and the storage devices like your eMMC flash or your SD storage. So the i.MX processor offers hardware encryption through the cryptographic accelerators and this iAssurance module CAM, which supports your Linux kernel driver. This CAM module supports the secure memory, the cryptographic authentication, your random number generators, all are taken care of on this layer. And from here is what the iWave security suite brings in the keyring. The keyring enables these interfaces to allow access the keys and perform operations such as the add, update, and delete from the user space. The CAM is instructed to use a black key as an encryption key. The CAM automatically decrypts the black key and places it directly into a key register before using the decrypted value in the user-specified cryptographic operation. From the Linux kernel point of view, the intermediate operations are opaque and there is absolutely no visibility. A Linux kernel, the de-encrypt and the DM integrity configuration is used to enable virtually the encrypted block with integrity support. The configuration of the device mapper is performed using this DM setup. So how the iWave security suite helps you is with the complete APIs for these functions, and it gives the complete support for the different functions available to encrypt and decrypt your data. Then moving on to your WOLFSSL TLS library. So what exactly is WOLFSSL before I get a bit deeper? The WOLFSSL is a lightweight, portable, C language-based SSL/TLS library targeted at your various IoT applications or your embedded applications. And TLS is now the successor protocol to SSL, which is a secure sockets layer. And TLS pretty much works the same way as SSL, except that we use encryption to protect the transfer of data and information. So the iWave security suite integrates this TLS 1.3 libraries with continuous update of various TLS libraries, which and completely takes care of the TLS integration with your i.MX platform, with APIs available to easily use these TLS libraries in your complete embedded solution. Now we're going towards the MENDER OTA update. So for system level updates, we require a dual A/B rootfs partition on the device. This ensures that the device can recover if the deployment is incomplete or corrupted during installation for any reason. So if the boot succeeds, then MENDER sets the updated partition to boot permanently when MENDER starts as part of the boot process. And when the MENDER client downloads and installs the images, other applications on the device continue to run as normal. So the security suite has integrated MENDER OTA. So on the field, you want to do an application level update, a firmware level update, or a complete system level update. This has been integrated in the security suite where we take care of your complete partitioning requirements and make sure that the OTA update happens in a smooth function. And OS hardening. So where I previously mentioned that you would definitely want to reduce the surface area open for possible attacks, correct? So depending on a custom configuration of your embedded device in terms of the wired connectivity, the wireless connectivity, the packages necessary. So the security suite enables you to easily customize your platform and reduce the OS space so that you're less prone to attacks, and you also have the complete log of the activities of the user through the security suite. Like now going a bit deeper into Opti, like definitely Silvano did mention the Opti for Android and Linux support on the NXP and i.MX SoC. But what exactly is Opti? So the trusted execution environment is basically an environment where the code and executed and the data accessed is isolated and protected in terms of confidentiality. So it adds like a layer of security where the code or data running on this trusted environment cannot be exposed to this normal environment. For example, you might have the Linux or the Android running on this layer, which is completely opaque to your secure world. So the transition from the secure world to the non-secure world is through this dedicated instruction called the secure monitor call, the SMC. When this instruction is executed, the CPU or the i.MX platform will enter in monitor mode and will have access to all the hardware features, including the protected peripherals, memory regions. And at this moment is when we can run the complete trusted environment or the operating systems. So for applications such as your voting machines or your point of sale machines where you have a touch screen and then you have the complete PIN details and your passwords. So that is a key example of where there is a key differentiation between your normal world and your secure world. So your touch forms a part of your normal world, whereas the complete features required to establish the connectivity is taken care of in the secure world. Moving on to Wi-Fi security. So there are a few key modules in Wi-Fi security, and with now the IoT device connected to different components. So like there is the 802.11w and the 802.11i standard. You have your firewall and the network intrusion detection system, and you have your Linux kernel where it takes care of the access control. So going a bit deeper into these different layers, the 802.11i, also known as the robust security network, it provides for different sort of sophisticated authentication using a variety of protocols with different encryption methods. And 802.11w provides protection in 3 key categories in terms of your management frames, or like your communication between one access point and one client, or communication between multiple clients. So by reporting network topology and modifying client behavior, so this helps you to prevent DDoS attacks against the network. So the security suite helps in configuration of these two security layers on your Wi-Fi device. And now coming to your network intrusion detection system and the firewall. So this is implemented through a SNOT feature. So the SNOT feature and the firewall feature are implemented as system daemons. The SNOT daemon becomes active automatically whenever the Wi-Fi interface is up and running. And this will ensure like a seamless security and deburden the user from the task to enable the detection system. Similarly, the firewall service is enabled with the system boots with a default drop policy or are highly portable according to the user system requirements. And that here comes the WPA supplicant. So your WPA supplicants such as the scanning, authentication, and association. The WPA supplicant runs in user space, which internally communicates with its kernel space through sockets. So in a high level, there are various levels of Wi-Fi security which need to be taken care of depending on the security required, depending on the sensors, depending on what type of access control you want, and the password control you require. And definitely a key feature which is often looked at is the access control. So for example, you might want to set different modes for different partitions. So the security suite helps you in easily helping create the profiles, different profiles for different personnel, the set modes, the get modes, and the disabling profile. So an application can be removed from the Mac control by simply deleting the profile. So without going through much software development, the security suite helps you in bringing this access control with absolute ease. Now, having gone through the complete software features available, let me just touch upon a case study. So iWave specializes a lot on the connected automotive space. And we would like to touch upon a case study where we did the complete security from the ECU all the way to the cloud communication. So the telematics control unit involves secure features, the vehicle interfaces, the infotainment platforms such as Ethernet, and the various hardware interfaces. And from here, it passes on to the vehicle interior interface where you have the different cables going on, where the CAN communication or the Ethernet communication and the different protocol stacks. And from here, you have the TCU or your infotainment systems, which have your event logging, the access control, or your firewall. And last but not least is your AI or your analytics, which runs on the cloud. And with now more and more cars being connected to the cloud, there is a need for this complete security to be taken care from the ECU to the cloud. So what can be the threats in your automotive industry? So these are listed as the key features. For example, you have close to around 26 microcontrollers in your ECUs, what you call it, within a car, and multiple sort of different telematics gateways through your infotainment engine or through your networking gateway. So you need to take care of complete software execution on the different layers of your connected car architecture. The same applies in terms of your data storage, in terms of on your ECU or in terms of your gateways. So what is the data you're storing and what is the level of confidentiality of that data? And one looks like to be very simple, but a simple action such as the TCU opening, like a telematics gateway opening to put a micro SIM inside the connector, this might completely open up your connected car to hackers, correct? So even like your mechanical parts cannot be excluded as part of your security design. Similarly, the data transmission using Wi-Fi, misuse of cloud credentials, and maybe even your JTAG. So being unprotected, anyone can flash a firmware tomorrow when the car is on the streets. So these are the different threats on a very high level. And what we have covered with our security suite is a solution to each of those threats. So the flashing using secured signed images, make sure that your unauthorized software execution does not take place. So be it the ECUs or the different types of gateways, the complete firmware is signed and make sure that the right firmware is executed on your different gateways. Data confidentiality and integrating using the different using the different signing mechanisms, your encryption mechanism, and the complete key generation and management. So this is what needs to be taken care of from your data confidentiality perspective. Tamper detection. So having a pin connected to your, having the pin of the processor connected to the enclosure, you are made aware of any intrusion into your mechanical or the complete enclosure point of view. And from your cloud connectivity point of view, you have the TLS libraries, your secret keys, or the device provisioning with complete tokens. So with these solutions to solve the problems listed on the previous slide, we have been helping various automotive OEMs secure the ECUs, and this is just an example. So the same concept can be also applied to your industrial or medical systems. So how do you get started with that development source? So definitely, security is a big ocean, and it's unless you categorize the features and get the complete security mapping done, there's definitely a lot of, like, how do you evaluate the secure boot? How do you evaluate the secure storage? So what we do is we have the security suite development kits where all our functions are integrated on the different i.MX8 platforms, ranging from the i.MX6 UL to the i.MX8M to the i.MX8 CordMax. So the table with Silvano presented lists the complete security functions available across the different processor layers. And the development kit, definitely there are 3 packages available. So you can get started the evaluation package where you have the secure boot storage, where you're able to evaluate the functions available on the i.MX SoC. Or if you have a custom design, where definitely it's a OS hardening, or Opti is definitely custom product. It's not like an off-the-shelf solution. So any starting from the security suite basic package all the way to the custom development of security for your end product, iWave has built the security suite to completely enable features for your security solution dependent on the features you require or the security you require. So that's it from my side. And so Silvano has given a good introduction of the features available on the NXP i.MX platform. And hope you have got a good introduction of the iWave security suite, the different security functions available, and how the security suite helps you integrate security without going deep into the processor architecture, and how you can speed up your product development.
So, well, that's all the questions that I see here in the chat box. In case you have any more queries, feel free to write to us. That's all for now. Thank you, everybody, for joining us today. Hope all of you enjoyed this session.